Thank you. Thank you for the introduction and the invitation. It's a great pleasure for me being here today. So thank you for giving me the opportunity. As Lena was saying, I will be talking about two possibly undetected populations of black holes, one very far away. So we're talking about quasars, and one very nearby, possibly in our own Milky Way galaxy. So yes, we all know that black holes occupy a very wide range in mass distribution. So typically stellar mass black holes up to 100 solar masses, or depending on the definition, of course, and supermassive black holes from 1 million solar masses up to 10 billion solar masses, typically the black hole mass that the largest quasars have been detected so far. So in the middle, there are intermediate mass black holes up to 1 million solar masses. They are more challenging to detect. They are usually found in dwarf galaxies. And today I will be talking mostly relating to supermassive black holes first, and then intermediate mass black holes. So a very brief cosmic history of black holes. We are now about 13.7 billion years after the Big Bang. The peak of black hole activity, so the quasar era, was about 2-3 billion years after the Big Bang, while the first supermassive black holes, or quasars, are detected now around redshift 7.5, 7.6, so less than 1 billion years after the Big Bang. While the black hole seeds, so the first population of black holes, was typically formed in the dark ages, so typically between redshift 20 and 30. So today I will be talking about one population at redshift higher than 6. We're talking about quasars, billion solar mass scale. And for the reasons that I hope will be clear in the next few slides, they are typically known as phantom quasars. The second population that I will be talking about is at redshift 0, so basically in the Milky Way galaxy, and they are intermediate mass black holes. So I will be giving a very brief historical overview on the detection of lensed quasars. Then I will be talking an observation that I was very lucky to be part of a couple of years ago about the first strongly lensed quasar in the epoch of reionization. And then I will be talking about 3 projects that are also ongoing, partially ongoing, about the detection of high redshift quasars. So I thought it would be interesting and fun to start with the first occurrence of the world's lensed quasars on NASA ADS. We are in the 1971. And this paper, I just want to point you out to this quote, to this sentence. It says that quasars are not novel constituents of the universe, but merely bright compact objects which have been focused and had their brightness intensified by a galaxy situated along the line of sight, acting as a gravitational lens. So basically they are saying that quasars are not special, and they are compact objects. They are so bright only because their light has been magnified by a lensing galaxy that is in between us and the quasar itself. Nonetheless, the first clearly lensed quasar was discovered a few years later. We are talking about a quasar at redshift 1.4, so relatively close for modern standard. And other quasars were discovered next quasars were discovered after 1979. But a couple of years ago, I was part of this team led by Xiaowei Fan, which discovered the first gravitationally lensed quasar in the epoch of reionization. So this is a beautiful source, and it's magnified by a very large magnification factor, about 51. So this is a quasar that is very far away. It's in the epoch of reionization, and by chance, it has a galaxy that is located in between approximately us and the quasar itself. So for that reason, we see multiple images of this quasar, and also the brightness of this quasar is very magnified. So the preliminary observations, this is with a ground telescope, LBT, didn't clearly state that this was a lensed quasar. It's basically unresolved. You can't really say that this is formed by multiple sources. You can say maybe that there is a little deformity here on the east side, but you can't really say much more than that. What we could say since the beginning is that this quasar was ultraluminous. At discovery, this was the brightest quasar ever found in the universe. It's the red star here. with a bolometric luminosity of 3 × 10⁴ per second and an estimated black hole mass of 5 billion solar masses. And I reported here some other famous quasars, including the farthest one detected so far, one in 2021. While these contours here are lower redshifts, low on quasars, and you can see here that also fractions of the Eddington luminosity are reported. So here, this quasar is extremely bright, it's super Eddington, and it's brighter than the brightest that were found so far. So now, this is the spectrum that we actually took with Xiao at the Keck Observatory with LRIS. You can see this is a beautiful spectrum. You can see the magnesium line here, with which the black hole mass, for example, was estimated. But yes.
What is the luminosity when you correct for the magnification?
Yes, I will be there in 3 slides. And it's a factor of 51 less. So I just want to point you out to this part of this spectrum, which is surprisingly enough the most important one for what I'm going to tell you. So let's zoom in this part. And you see, this is the part where you don't expect light from the quasar because it's well inside the reionization epoch. There is a lot of neutral hydrogen between us and the quasar itself. You can see here some IgM transmissivity spikes. So it's transmissivity windows of the AGM that still allow some light to pass. But here in the deepest part of the Gunn-Peterson trough, where you really don't expect any light from any source at redshift higher than 6 approximately, you see some weak continuum emission that it shouldn't be there. So this is what led Xiao Yifan to request some Hubble Space Telescope imagery for this source. And as you can see, we have a much clearer view of what this source is really like. Here on the right side, you see maybe 2 sources that are kind of clear at this point, A and B. And on the left side here, you see maybe another source that we identified as G, so galaxy, a little spoiler, for the reason that I will be telling you now. So why do we say that this source maybe is a galaxy? Well, what you can do is that you can take a picture of the same image with a filter that is centered in the deepest part of the Gunn-Peterson trough. So you remove anything that is at redshift higher than 6. And what happens is that this image transforms into this image. So the quasar completely disappears and you remain with sources that are a lower redshift. So before, after the reionization ended. So this is the reason why this source was called G, so a galaxy. And the best fit model that was done by other people in the collaboration calls for a redshift of the source, so the quasar, a redshift 6.5, a redshift of the lensing galaxy much closer to us, a redshift 0.7, and this galaxy is also it's very small. It's a 10⁹ solar masses quasar. So at detection, this was the galaxy. So this was the lowest mass quasar galaxy acting as a lens for a quasar that was detected so far. So this is the fiducial model. As you can see, we should be able to see 3 images, but actually 2 of them are too close to each other to be actually visible. And the maximum separation between this source and the farthest source is about 0.2 arcseconds. So it's very close to the Hubble Space Telescope resolution limit. And the model calls for a total magnification of 51. 51 magnification. Yes.
10⁹, that's the dark matter and the visible matter. And is that sort of consistent with the apparent flux of the galaxy? Like if you do the stellar to dark matter mass, it all looks good?
I think that the 10⁹ is only stellar mass.
Oh.
Yeah. And it's consistent with the model. So, you know, actually understanding characteristics of the lensing galaxy was maybe the most complex part because we don't have much flux from the galaxy, but we did, Xiao Yifan did other follow-up observations that are basically confirming this model. So it seems like quite a small galaxy for how much magnification it takes.
Also, if you get a lens galaxy is usually more near the center of the images rather than all on one side.
Yeah.
Something strange in the geometry.
It is a little strange, and you know, it's close to the caustic line of the model itself. That's why the magnification is so large. So it's just a chance, and this chance was actually lucky, as I was showing in a couple of slides, because if the magnification was not 51 but was about 20, we would have never selected this quasar as a high redshift quasar. It would have been completely neglected in pre-selections. And this is what I'm going to tell you in the next few slides. So to answer your questions, if you consider that this source is magnified by a factor of 51, the intrinsic properties of the quasars shift the quasar in a much more common position in the black hole mass versus bolometric luminosity, and a bolometric luminosity of 5 in 10 to the 46 per second, and an estimated black hole mass about 500 million solar masses. So this quasar is, you know, it's interesting, but it's not as miraculous as it appeared at the beginning. So building on this lucky chance of having a quasar that is so intensely magnified, we built a lensing model to actually compute probabilities of magnification, to ask questions how likely it is that it was so magnified. So I will be describing this plot little by little. On the horizontal axis, there is the log of the magnification factor. On the vertical axis, there is the probability of obtaining a magnification factor that is higher than a certain value on the x-axis. This is the magnification of our source, 51.3, and this is the frequentist probability of finding a quasar at redshift higher than 6 that is lensed. So far, thus far, we've detected about 200, 250 quasars at redshift higher than 6. And still today, this is the only lensed quasar in the epoch of ionization. So this is basically 1 over 200. Now, I don't have time to go into details of the model, but please feel free to ask me questions now or later. I just wanted to point out that the quasar luminosity function was modeled as a double power law, and the bright end is parameterized by beta. Beta is always positive, so the larger is beta, the steeper is the luminosity function. So why I say that? Because beta is the main parameter of the model, and considering a shallow value of beta, 2.8, which is quite common in literature, this is the lensing probability distribution that we find, and in particular, the probability of strong lensing is about 4%. And using another steeper value of the quasar luminosity function, 3.6, also very common, you see that the probabilities are higher, and the probability of strong lensing is about 20%. Now, regardless of the specific value of the quasar luminosity function's bright end that you choose, what I want to point out from this plot is that you do expect more lensed sources at redshift higher than 6 than the only one that we detected so far. And this is true especially at mild magnifications. So we don't really expect that magnification 50 or 100 is very common, but we do expect that we should be finding more quasars that are magnified by lower magnification factor. So everything above this line is what we call the phantom quasars. So these are quasars that redshift higher than 6 that should be magnified even by small factors, but we haven't found them yet. So why can't we detect them? So as pointed out in the original paper, there could be a selection bias in photometric surveys against lensed quasars, and I will be talking about that now. Or as we also proposed, the separation between images is unresolved, even with the HST. So even if you see a quasar and you can't really see a double image or multiple images, it's very hard to say that this quasar is lensed. So why are they misclassified? So point one of what I was saying before. So imagine this is a quasar. This is actually a drawing that I did about 15 years ago. And say that you are, yes?
Sorry, this is better here. So I guess it's correct. We don't have any measurements of time delays. Is that correct?
No, we don't have measurements of time delay for this. Yes. So imagine that this is a quasar for a moment, and imagine that you are doing a photometric selection, a photometric survey to pre-select quasars at redshift higher than 6 that you're interested in. Say that you also have the spectrum of this quasar. So this is the actual spectrum that we took with LRIS. Now, if you want to pre-select this quasar as a high redshift, redshift higher than 6 quasar, then you need to have a very large dropout between the pre-Lyman alpha and the so-called dropout bands here indicated in yellow, so after the Lyman alpha. But the point is that if you have a galaxy that is in the same photometric aperture, then the galaxy is having some flux here. And this can actually fool your selection criterion. So maybe you are just observing this quasar in a photometric survey, and you see that there is not a very large dropout, and you say, okay, this is not a quasar redshift higher than 6. So actually, we did some simulations. This is still the actual spectrum. And if we reduce the magnification factor from 51 to about 20, you would actually see that the current selection criterion for quasars would not selecting this source as a quasar. So it's possible that high redshift length quasars are misclassified into low redshift galaxies or low redshift whatever. So they're not interpreted as being in the ionization epoch. Of course, if you take the spectrum, then you realize it's a quasar, but you need to take the spectrum for that. Another possibility is that the separation between images could be unresolved. So this is a plot, a cumulative plot, and I'm showing on the horizontal axis the separation in arc-second. This is the fraction of sources at redshift 6.5, so approximately where the other quasar was found, that have separations larger than values on the x-axis. So as you can see, we do expect that for a typical quasar redshift about 6.5, about 15% of these sources should have separations between images that are completely unresolved, even with the HST. So this is a second order correction, but it's still possible that we are still missing some sources for this. So one possibility that we pointed out is that the Roman Space Telescope, as it was called at the time of the paper, the w.r.t.gas, with a PSF that is about 0.1 arc-second, so very similar to the HST, but it has the advantage of having a very larger, much larger wide area survey. So it's possible that with the Roman Space Telescope, we will be finding some more interesting sources like this, and we can better compute statistics for this kind of sources. So as we were saying, it's possible that the Roman Space Telescope will act as a ghostbuster to find some of these phantom quasars. So this is another project that we started with a student. She's a senior student, Lucia Gordon, and also with a postdoc in Stanford. So we were searching for lensed quasars with Chandra using a very interesting code that I will be describing right now. So remember this picture. This was led us eventually to understand that this source was lensed with multiple sources. So we're trying to do the same, but with X-rays. So let me explain you what we're trying to do. So we're using this code that was developed by Adi Ford. Again, she's a postdoc at Stanford. And this code, Max, was originally developed to find dual AGNs. So we're talking about AGNs that are really physically dual. So they are two supermassive black holes that are inside the same galaxy. So of course, the code doesn't know if these are physical AGNs, dual AGNs, or there are multiple images of the same quasar itself. So we're trying to use the same code that is based on a Bayesian analysis, including also the PSF of Chandra. So it's a very complex code. It actually is able to give probabilities, so Bayesian probabilities, on the image being created by a single source or a double source. So as you can see, these are simulated images, and the ones that are blinking here, they are actually dual AGNs. But the point is that you can't really see by eye. And this is what we are trying to do, even with images of quasars at a high redshift that are we would never be saying that they are dual or they are lensed, just looking at by eye. This code is actually able to understand, or at least to assign a probability for them being lensed. So we actually search for multiple images of quasars in a catalog of 22 sources, a redshift 6.5. This is a recent catalog by Lee in 2021. And we found some suspense, exactly 0. So we found out of 22 sources, we found exactly 0 sources that are clearly lensed, so at 3 sigma level. We found 4 marginally positive sources, meaning that the probability of a dual image is 50% more likely than the probability of a single image. But we did a lot of testing with this code, and this level of Bayesian probability is not enough to claim a clear detection. Nonetheless, we used this study to put some constraints on the steepness of the bright end of the quasar luminosity function, and we were able to put an upper limit of 2.98 on the beta, which is quite useful because it rules out one of the 2 most common values in literature, while leaving the other one still feasible. So the question is, how many phantom quasars are out there? So we try to answer this question with this plot. This is a probability. This is on the x-axis. Is the probability? Yes.
So you mentioned that you search for this lens system, like out of 22 quasars. So where are these 22 from? Are they from Slomo?
These are Chandra quasars. They are all Chandra quasars. I believe they are also observed in SLO1. Yes. This is a paper that came out, I think, in January or February this year, and it has more quasars than this. They are not only 22. We selected only the ones that are redshift higher than 6.5. They have multiple images in Chandra. So we did a further selection to actually improve our possibilities of finding one. But we didn't find none. We didn't find any, so it happens. But it's still interesting. So it points out that the quasar that we found a couple of years ago, it's special for some reason, and we still need to understand why it's so uncommon to find them. So
and when you check whether or not they are lensed, it's only based on the X-ray
yes.
data, not other things. So is there any reason why Chandra only is better by compared to combining?
Yes, so you're completely right. Chandra has a worst angular resolution, the HST is 0.1, Chandra is about 0.4 arcseconds. Besides, Baymax was written for Chandra images, and we could use exactly the same code, and we did a lot of testing to see if we could actually detect anything of any quasar that is lensed at redshift 6.5. And also, this code provides you with information about how the sources are organized. It provides you with the separation between the 2 sources. It provides you with the apparent brightness, so the ratio of brightness within the 2 sources. So we use this code first because we have clear detections of sources from Chandra, so they are clearly AGNs, and also because we could use this code that was built from for Chandra, and it's very good at assigning probabilities of lensing or not. So also these sources, they don't appear to be lensed in the HST. Some of them have HST images, and we check them, and they don't appear to be lensed. So it's as much as we can do so far.
Yes. Okay.
Yes.
So if you only have 22 sources, is there any theoretical prediction for how many of those sources you expected to
Yes.
have this behavior? And then also, I'm just trying to understand, do you believe that based on what you were able to do with Baymax, none of those sources are lensed, or do you think that there's still potential sources even within these 22 sources that could be lensed, but you don't have enough information to tell?
Yes, so very Very important question. So based on this lensing model, out of 22, we were expecting that at least 3 to 4 should have magnification factors lower than 10, probably. So they are strongly lensed. It remains to be seen if any of these sources are lensed or not. As I said, there are 4 sources that are marginally lensed. So this could be a call to make more observations about this, not with Chandra, because we can't do much more than that with Chandra. One of them had also HST images, and it doesn't seem to be lensed at all. I think other 3 sources didn't have HST images, so we are thinking about maybe doing a proposal for that.
Is there anything you could do with SDSS data to tell for those sources, or is it not really useful for this?
I don't know. I'm not sure about this.
Okay, thank you.
Yeah, I'm not sure about that.
SDSS typical seeing is 1.2 arc seconds.
I was thinking maybe if they had like a spectrum.
Well, they probably are also selected spectra. The vast majority.
But you think
of
that the
them-
resolution in the spectrum is not going to be high enough? Okay, I'm not an observer, so I don't.
Right, yeah, no, what are you trying to do with the resolution?
I was just wondering if the Sloan spectrum would be useful at all. And I could be completely like
I
shot in
mean,
the dark.
the stuff that Fabio described with seeing the lensing galaxy requires much deeper spectroscopy, I
Okay.
think, than
Okay.
what Sloan can do. Those were Keck, right? The ones.
That's
that you
the
said.
spectra is Keck, yes.
Yeah,
Okay, thank you.
So I was saying that we're trying to figure out how many phantom quasars are out there. And this is a plot that shows the probability of strong lensing, and it's exemplified by some particular values of the brightness of the stiffness of the bright end of the quasar luminosity function, from shallow values 2.8 up to extremely steep values about 4.5. And this is the ratio of undetected over detected populations of quasars at redshift higher than 6. So meaning a value of 1 means that the undetected population is equal in number to the detected population. So just to give some number, let's consider a number density of about 1 per gigaparsec cube of quasars at high redshift. If you consider a shallow value of the quasar luminosity function, the bright end, you see that there is a very small correction. It's about 3% of the known population of high redshift sources, which is very possible. I mean, I would be surprised if we found exactly all the high redshift quasars. The problem is that if you go to steeper and steeper values of the quasar luminosity function, the bright end, reaching 4.5, this was actually proposed by Kulkarni in 2019, you see that the corrections needed are extreme. They are 12 times the known population of quasars. Now, the presence of so many undetected quasars at high redshift is quite unbelievable. So I don't personally believe that, also because it would be problematic for some constraints from cosmology, etc. But nonetheless, you have a question?
okay, yeah, so I'm trying to understand why that is. So you're normalizing the bright end of the luminosity function by saying we have observed X quasars and therefore the bright end of the luminosity function is normalized. Then you are, if the slope is very steep, then that means there's a huge number of faint quasars, and it's just a numbers game, meaning that there is an extra probability of these objects being lensed.
Yes.
Right? But that is normalized. That statement is normalized at the bright end.
It's normalized at the bright end.
Okay.
Yes. Yes, so I was saying, nonetheless, studying high redshift quasars, being them lensed or not, is very important for understanding their contribution to organization, their contribution of dark matter, if any, and in particular for what I will be talking in the next few slides, for understanding the population of high redshift black hole seeds. So the first population of black holes that were formed at redshift 20 or 30. So what we were proposing to do is to predict how future detections of, yes.
So before we leave that specific object, so do we have any other understanding about that high redshift lens quasar? For example, its black hole mass. So it seems that you're correct for its magnification, but can we do the black hole mass from its spectrum? And do they consistent?
Yeah, actually, a black hole mass is computed from the magnesium line.
Okay.
Yes. So so when the red, you remember the red star was shifting. Okay. So the brightness was corrected by the 51. Then the spectrum was corrected to take into account that is magnified by 51, and then the black hole mass that shifted from some billion solar masses to 500 million solar masses was recalculated from the magnesium line.
Okay.
So we already did that. So this is a zoomed in version of the previous history of the universe plot, zoomed in the dark ages and the reionization. Currently, the highest redshift quasar detected so far is a redshift 7.6. It's a very recent detection. And current models call for the farthest quasar of 1 billion solar masses that is detectable around redshift 9 to 12. And this is also considering Euclid surveys, etc. So while the first population of black hole seeds was formed likely around redshift 20 to 30. So what we were proposing is that if we push the detection limit of the farthest quasar to higher and higher redshift, possibly to 9 and 12, you see the time between seeding and detection is shrinking. And we calculated actually how this can contribute to understanding and constraining the parameters of black hole growth. So we basically studied out the impact of future detections of high redshift quasars, redshift higher than 8, to constrain the parameter of black hole growth and seed models. So this is quite a simple model. It's based on a Monte Carlo simulation with a target function that is given by this classic formula of black hole growth. This is the black hole mass computed at time, cosmic time t. This is the initial mass of the seed, and we will be considering light seed up to 1,000 solar masses and massive seeds from 1,000 to 10 to the 6 solar masses. This is the Eddington ratio. So the ratio between accretion rate and Eddington accretion rate. This is the duty cycle, so the time spent accreting. This is the radiative efficiency. And this is the time spent accreting. So it's the time between seeding and detection of the quasar. While this is just a combination of parameters, about 450 megayears. So these are the 4 parameters that we considered in the Monte Carlo simulation. And a single run of the Monte Carlo is successful if 10 to the 9 solar masses quasar is formed by the detection redshift. So we did this experiment starting from the highest redshift quasar, redshift 7.6, and this is about 1 billion solar masses object. So this is a corner plot. This shows the dual distribution of parameters, and on the diagonal you can see the marginalized distributions. As you can see, a redshift 7.6. This is not very helpful to constrain most of the parameters. You can see that high black hole masses are favored, but also lower black hole masses are still possible, as also intermediate values of the Eddington ratio and duty cycle itself. So if you go to higher detection redshift, about redshift 9, the situation slightly improves. It doesn't improve that much. You can see that high masses are still favored, but also lower masses, about 10 to the 4, 10 to the 3.5 are still possible. And you see, as I was saying before, also the accretion, the Eddington ratio and the duty cycle are still favored to be very high, although intermediate values are not completely impossible. What becomes interesting is that if you go at redshift 12, then this becomes much more pronounced, meaning that high mass seeds are strongly favored. It's almost impossible to form these sources with lower masses, and also high values of the Eddington rate and the duty cycle are strongly favored in the model, and also very low values of the radiative efficiency compatible with the lower bound for slim thin disk accretion are needed. So we call this, yes.
do you have a strong prior on the Eddington luminosity? Like it seems like you are.
Yes, so it's in the next slide. So this is a completely, as this slide is saying, this is a completely blind estimation. We have very broad flat priors on all the parameters that we consider so far. What we are doing, what I'm showing in the next slide is what happens if we also consider some priors on the Eddington ratio itself. So as you can see, uncertainties in the blind estimation, if you go from detection redshift 9 to 12, decrease by a factor 3 to 5. So what we're saying is that even if you don't know anything about the quasar, so the growth parameters, you just are able to compute the black hole mass, then going at higher and higher detection redshift will automatically help you in constraining how this black hole grew from the seeding to the detection, just because the time between detection and seeding is shrinking progressively. So what we did to answer your question is also to consider some priors on the Eddington ratio. In particular, we considered 8 quasars at redshift higher than 7, for which an estimate of the Eddington ratio is provided along with some uncertainty, and we consider that as a prior. So as you can see, for most of these sources, this is a radiative efficiency versus black hole mass seed estimate. This is not helping much. It's you can see there is a wide variation between black hole seed masses and radiative efficiencies. But if you consider only these 2 sources, which have lower values, estimated values of the Eddington ratio, these 2 sources are actually called low luminosity quasars by in their papers. You can see that by assuming some priors, some strong priors on the Eddington ratio, then you can actually much better constrain the parameter space for the mass of the seed and the radiative efficiency. So not only going to higher redshift, but also having some quasars that are lowly accreting, it can help you in fixing, in constraining the parameter space. So this is a summary of the first part, and no worries, the second part is much shorter than this. So we might be missing many phantom quasars because of misclassification, or they are small separations. In future wide area surveys and re-examinations of some of known sources may be needed. Then higher redshift detections of quasar will constrain their growth parameters in blind estimations. And this is even more important if we have some priors on the Eddington ratio and or radiative efficiency for these quasars. Now, in the last 10 minutes, I wanted to describe 2 projects that I did with 2 incredible students this summer, and they are related to possibly nearby intermediate mass black holes. So the first project is about IMBH dynamics, and this was led by Emma Weller, class 24, and also in collaboration with Lars Ehrenquist and Sona Bose. And the second one was related to the irradiation properties of these sources. And this was led by Brian Seapol, class 23, and also with Ramesh and Don Pesce. So a little introductions. We know that in the Milky Way galaxy, there are many stellar mass black holes, maybe 10 to the 8 stellar mass black hole. There is one, at least, supermassive black hole at the center. Fortunately, it's not shining that much as in that illustration. And we also know that smaller galaxies have also smaller black holes at the center. This is standard correlations. So intermediate mass black holes are found commonly now in dwarf galaxies. This is an archetypical intermediate mass black hole of 50,000 solar masses found by Vivienne Baldassare in 2015, and in RGG 188. And so how can intermediate mass black holes end up in the Milky Way galaxies? There are several.
These intermediate mass black holes in the dwarf galaxies, you say these are routinely found now.
Yes.
Is that obvious? Are they, like, would you say there's a smoking gun that they're definitely there? Because doesn't it assume something about the stellar dynamics in the center, the distribution function?
It's just that it's more challenging to detect them because they are lower luminosity, and many times they are confounded with star formation that is also in the dwarf galaxy. So, also star formation is emitting some X-rays. So sometimes even with the Chandra, you can't really discriminate if there is a black hole at the center or if there is just the galaxy itself. So it makes sense that for standard correlations, if you have a smaller galaxy, you have an intermediate mass black hole in a dwarf galaxy.
Correlation certainly makes sense.
Yes,
Like I
makes
say,
sense.
These are not really.
What's the occupation fraction? I think is what Chris is asking.
Oh, yes. So we actually made a paper recently about occupation fractions of massive black holes in intermediate mass black holes. And we found that the active fraction, which is slightly different from the occupation fraction. So the active fraction is the fraction of intermediate mass black of galaxies that contain an intermediate mass black hole that is actually accreting. And we computed about 30% of active fraction for most massive dwarf galaxies. Current X-ray data, so X-ray detected occupation active fractions are much lower than that. They are about 5 to 6%, I think. So this is calculated from Chandra data. But we made a model in this paper, and we are suggesting that the active fractions should be higher than that.
Your definition of IMBH is anything under 10 to the 6.
Yes. Yes, because usually supermassive black holes start from 10 to the 6. It's just a definition at the end. It doesn't really matter. So as I was saying, there are different models for how intermediate mass black holes can be created or led into the Milky Way. And in particular, we focused on one of the propositions, so a dwarf galaxy that contained an intermediate mass black hole at the center, at some point merged with the Milky Way galaxy. And for that reason, the intermediate mass black hole is still wandering in the Milky Way itself. So the Milky Way should have experienced about 15 mergers with galaxies with stellar mass larger than 10 to the 7. And there are also several recent papers that are studying the possibilities of the possibility of having intermediate mass black holes or even some supermassive black holes that are just wandering in the Milky Way galaxy itself. So for the first project, the dynamics project, we used some cosmological simulation, in particular the Illustris TNG50, which is the highest resolution run in the Illustris TNG. And I don't have time to go into the details of how we selected proxies. I just have to remind you that in the Illustris TNG simulations, there are no intermediate mass black holes. There are just supermassive black holes at the center of galaxies. So how do we simulate intermediate mass black holes? We use proxies. So we use the objects that are star clusters with the mass in the correct range. And we are assuming that the gravitational effect on large scales that are much larger than the softening length, I have problems with the H sometimes. It's similar to what we should expect from intermediate mass black hole. So we selected these proxies that are located at the center of mass of a dwarf galaxy that eventually merged with the Milky Way galaxy, and we followed their trajectory and studied the dynamics. So some results that I will showcase right now. Perhaps on, yes.
I'm a bit confused. Like I thought the resolution of star particles was around 10 to the 5 solar mass for TNG.
No, I think it goes down to 10 to the 4 in the Illustris simulation. Yes, so it's, we don't find anything in the 10 to the 3 solar mass scale. Yeah, this is just a range in which I was considering intermediate mass. I think it's about 10 to the 4.
What is the typical softening length?
250 parsec. And we studied lengths that are bigger than kiloparsecs. So we are considering a factor 5 larger than the typical softening length for these objects. You have a question?
No, carry on, sorry.
Okay, yeah. So perhaps unsurprisingly, intermediate mass black holes are sinking. So we found that about 84% of the population studied is sinking. So as a long-term negative radial velocity, and about 13% of them are found at redshift 0 in the central kiloparsec of the Milky Way. Now, just to understand what we did. We are not suggesting any particular number of intermediate mass black holes in the Milky Way. Okay, we found we selected all the proxies that we could. Some of the groups that we used are 5,000 intermediate mass black hole proxies. We're not suggesting that are 5,000 intermediate mass black holes or any number. We're just using this number as statistics to study their general properties, okay? So, and we found, I said, 13% in the central kiloparsec after an ample time. So after we wanted to study the radial velocity versus distance, so this plot, the points here are our intermediate mass black holes proxies. The blue line is binned, and this is a model fitted with a power law. And you see, this is the distance from the center of the Milky Way analog. This is the long-term radial velocity. So what you can see here is that it seems that with decreasing distance towards the center, the radial velocity is tending to zero. So it seems like we are assisting to some kind of orbital circularization of intermediate mass black holes. So there are dynamicists here that know much more than me, so we can discuss about it. But for this project, we did a very simple physical model. We just considered a gravitational effect and a linear drag force to make some calculations. And we found, solving the equations, we found the trend of the radius versus time, and this is a function of a parameter, a non-dimensional parameter that tells you basically how fast the radius is shrinking with time. And with 4 intermediate mass black holes proxies, these are their masses. You see, we can see something about 10 to the 4 solar masses. These were fitted, and these are part of the sub-boxes at a higher resolution. So we are just suggesting that there is some sort of linear drag that is reducing the radial velocity with time, and it's circularizing the orbit as the intermediate mass black hole is sinking toward the center. So finally, for this project, we also studied the 3D velocity, both with respect to the Milky Way center and with respect to the galaxy. So it seems that most of these intermediate mass black holes are orbiting in the galaxy with a typical velocity of about 180 kilometers per second. The variance is increasing with decreasing radial distance from the center, and they are well fitted by Gaussians. But if you compute the 3D velocity with respect to the gas, so the local gas around the intermediate mass black hole, you see that the typical velocity is much lower than that. We expect typically velocities about 88 kilometers per second, and also the distribution is very skewed towards lower velocity. Yes.
How many Milky Way analogs do you have?
How many
Milky Way analogs do you have?
So in this set, I think we used about 4,000 in intermediate mass black hole. Analogs. 4. We used a catalog of Milky Way analogs that was provided by Annalisa Pilepic in the illustrious DNG project. And we studied the intermediate mass black holes proxies that ended up in this 4 Milky Way analogs.
So then to set your scales, I guess you normalize them.
We normalize to the same. We normalize to the same distance. Yes.
And then one naive question is like, why don't you then consider like zoom in simulations? They would have higher resolution. I guess you can.
We actually consider for some of these calculations we consider sub boxes, and they have a higher cadence of data dump. I don't know, there was a technical reason why we didn't use zoomed in simulation. I can't remember right now, but maybe we can discuss about it later. And yes, to conclude this part, you see, typical velocity with respect to the neighboring gas are much lower, and this may be important for accretion properties of intermediate mass black holes, because if the velocity of the gas around them is lower, then it's easier for the gas to fall onto the black hole. So this is precisely what we did in the second project that I will describe in the next 5 minutes, and then I'm done. So what we wanted to compute is, can we observe these intermediate mass black holes in the Milky Way? And if yes, in which bands or which instruments are more likely to observe them? So we used the classic Bond accretion model, and in particular the parameters that were changing, where variables are the density of the interstellar medium, the velocity of the of the IMBH with respect to the interstellar medium, the sound speed of the interstellar medium. And for this particular project, we assume that black hole mass that is fixed, it's about 10 to the 5 solar masses. We also consider some correction to the classic Bondi model to take into account convection and turbulence. So it seems from simulations that the Bondi model is not accurate enough. It provides accretion rates that are too large. And so we corrected this with this factor that leads to lower accretion rates. So we actually consider 5 Milky Way environments. So environments like the molecular cloud, the cold neutral medium, warm neutral medium, warm ionized medium, and hot ionized medium with their own molecular composition, number density, and temperature. And we also weighted our results for the actual probability of finding that particular environment in the Milky Way. You see, the molecular cloud is maybe, as we will see in the next few slides, the best environment to find an intermediate mass black hole because it's very dense, it's lower temperature, etc. But it's very unlikely. It's about 0.05% in the as a volume weighted in the Milky Way, while the hot ionized medium is the most likely to be found. So actually directly some results. These are computation of fluxes, X-ray fluxes, and this is a probability density. And there is a categorization in the 5 different environments that I was talking about before. So to make you understand these simulations, we are, again, not predicting any number of intermediate mass black hole in the Milky Way. We are just throwing randomly and uniformly 1 million intermediate mass black holes in the Milky Way galaxy. So some of them will end up in the hot ionized medium, some of them will end up in the molecular cloud, etc. We are actually weighting these environments to account for how likely they are in the Milky Way, and we are just computing the fluxes that they are emitting in different bands. As you can see, these are X-ray fluxes. And for example, the molecular cloud, that is the blue one here, is providing the higher fluxes because it's the densest environment. This is cold neutral medium, the violet one. So the Chandra should be able to observe about 10% of intermediate mass black holes, so 10% of fluxes potentially emitted by intermediate mass black holes, while Rosita should be able to observe 4%. We did the same for the infrared. This is the plot for the infrared, and the Roman high latitude survey should be able to observe 16% of these sources. Same in the sub-millimeter, the scuba, about 20%. And we did also a similar calculation for the future CMBS4, stage 4 future CMB experiment, should be able to observe 23%. And in the radio with the BLBA, should be able to observe 20% of these sources. And these are, yes.
Okay, you start with Bondi. I'm okay with that. But then let's say, even if you're in the dense environment, there is still a little bit of angular momentum. It will form a disk. It will not be an infrared source. It will be a UV X-ray source, right? So what are the assumptions that go into such high detection rates?
Yes, so
in the infrared band?
To actually compute these fluxes, we used a code that was provided by Gunn-Peterson. So this code is able to compute the spectral energy distribution for a black hole for which the black hole mass and the accretion rate was given. Okay, so we're talking about ADAF, mode accretion rates, so very low accretion rates. And in the code, they are considering both emission from the disk and emission from corona, etc. So it's possible that in the model we're still missing some characteristics of the black hole accretion, but I think that it's are reasonable assumptions that we're making.
Yeah, I think the key is ADAF. I mean, are these what is accreting as an ADAF? Is there anything in the universe that these codes can be calibrated against? Like,
no, the maximum Eddington ratio that this code can deal with is about 10 to the minus 5 Eddington accretion rates. So we're talking about lowly accreting black holes.
Okay.
And finally, these are the results in the 5 bands. And as you can see, they span about 28 orders of magnitude. Yes.
I have a nice question. So like, I think you mentioned this, but so how should I think of this? Like you are using like some small sub boxes of TNG50 and injecting artificially, like them artificially with these IMBHs?
This is not with TNG50. The first project, the dynamics ones, was with the cosmological simulation. This is a code that we wrote to, you are imagining to throw 1 million intermediate mass black hole in the Milky Way galaxy. You are dividing the Milky Way galaxy into 5 different environments that are volume weighted. And with the code that Gunn-Peterson provided, you are calculating, inputting the black hole mass, which is fixed, it's 10 to the 5, and the accretion rate, which is computed for the different environments. You are calculating the spectral energy distribution, and from the spectral energy distribution, you are getting the fluxes. So this is not a cosmological simulation. Sorry, I should have stressed that. And this is finally the results in the 5 bands, in all the bands. And as you can see, they span about 28 orders of magnitude in fluxes. So finally, we actually studied in different bands what are the ISM environments that are more likely to show intermediate mass black holes. I'm showing here the one for the Roman observability, so in the infrared, but they are very similar with other instruments. And as you can see, the molecular cloud has almost 100% observability. So the lesson is, if a black hole is passing through a molecular cloud, assuming a dimension of 100 parsec, it should have 1 million years crossing time, and it should be observable in basically every band. We're actually thinking about doing a survey with Ivan Del Vecchio, using actually data from a survey from Ivan Del Vecchio in Brera. This is a survey of 540 quasars in this redshift range, and it should be sensitive to brightness temperatures higher than 10 to 5 Kelvin. And we're trying to understand if in this survey we are able to detect some sources that are off-centered with respect to the central emitting source. So this is a summary of the second part. We said that about 84% of intermediate mass black holes are sinking, and 13% reach the central 1 kiloparsec within a Hubble time. So the most likely region to look for intermediate mass black holes should be the center. Orbit seems to circularize with time. Typical velocity with respect to the Milky Way center is about 180 kilometers per second, and with respect to the local gas is much lower. And a fraction of intermediate mass black holes are observable in all electromagnetic bands, from 10% in the X-ray to 20% in the submillimeter. And IMBHs are always visible, almost visible in molecular clouds, and partially visible with a 50-50% chance in cold neutral medium. So thank you very much.
Questions?
Okay, so I had a question about the first part of your talk. Is it possible that some of the discrepancy for these phantom quasars, is that possible that it's due to the uncertainties in the lensing model? And what are those?
So you're talking about the lensing model, the probability of lensing as a function of the magnification.
Yeah, I mean, I'm asking in part because, like ZTF, and this is looking, for example, for strong lens supernovae, but they're expecting on the order of 10-ish per year, and thus far we have none.
Yeah. It's very possible. I mean, in this lensing model, there are a lot of assumptions that go into, so from the distribution of galaxies, the distribution of dispersion velocity in galaxies that ultimately determine how is the Einstein ring, etc. So of course, there are a lot of assumptions. There are work papers starting from 2002, 2001 also. I remember Whiting and Leb 2002, maybe, that were predicting that up to 1/3 of quasars at redshift higher than 6 should be lensed by magnification factor lower than 10, lower than 10. So there are several models, not only ours, that are suggesting that just for the distribution of galaxies between us and these quasars, we should be able to observe more lengths. It's possible that we are overestimating them for several reasons that are in the model. It's very possible.
Next question.
Yes.
Can I ask a question? I'm on Zoom. Can I ask a question on that part of the modeling for how many lengths we may be missing? Did you try to use the cosmological simulation to do ray tracing to see how many lenses may be expected?
No, we didn't do any ray tracing simulations with cosmological. No, it's a good idea. We actually thought about doing that 1 year ago, but we haven't found the time yet. This is just an analytical modeling based on the distribution of galaxies between us and the quasar, and with some assumptions on the brightness of the slope of the bright end. It's just an analytical model.
So for the last part of the total, how about those intermediate mass black holes in global clusters? Like, so do they, like, which category do they apply to, or like in the last part, like different environments? So basically, the environments are very just gas poor, right? So
so we didn't focus on intermediate mass black holes in globular clusters. We were just assuming that they were formed in dwarf galaxies that ended up in the Milky Way, like a normal merger, and they're just wandering out there. And we used like realistic assumptions on the Milky Way environments to calculate what would be the fluxes for this. I mean, if these intermediate mass black holes end up in a region of the galaxy that is very depleted of gas, we're not going to see anything. Actually, most of the galaxy, we're not going to see anything if you think about the observabilities. You see, in this histogram that I showed you at the end, let's say the hot ionized medium, that is the most common environment in the Milky Way galaxy, is about 47% in volume. You're not going to see anything. So it's very possible.
Great. If I understand, you're using the proxy because your simulations, Illustris, doesn't have actual intermediate mass black holes in it. You're using something of a comparable mass as a proxy for that. So you're using the clusters.
Mm-hmm.
So, and then you derive from that some distribution of what the sort of radial, in all the different radial bins, how many intermediate mass black holes there ought to be. So,
yes.
Well, as a check of the dynamics, have you checked that actually matches the cluster distribution in the galaxy?
Yes, we actually checked that it matches the cluster distribution of the galaxy. Yes, this was actually a test that was suggested by Lars at the very first Zoom meeting that we had with Emma. Yes, Lars knows.
So can you like push down to like lower black hole masses than you have considered? Like 100 solar mass primordial black holes might be heating molecular clouds. And
yes. So to start with this project, as I was saying, we started with a 10 to the 5 solar masses black hole. So these are fairly big black holes. So we don't expect many of them. Maybe if you just assume a power law distribution in mass, as we were seeing yesterday with Lena, maybe we should find 100, maybe, or even less than that. Assuming that there are. If you consider 100 or 1,000 solar masses black holes, you should be able to find many of them. And we haven't done it yet, but it's certainly something that we can do. You expect a lower observability though, because you have lower fluxes probably.
If you put it with the numbers, like the number density.
We haven't done it with 100 or 1,000. I just expect that you will just rescale the fluxes. So because they are smaller masses. So.
There may be another problem, which is that these higher mass objects suffer from dynamical friction. They slow down, they agglomerate in the center. The lower mass objects will not suffer from dynamical friction as much. they will continue running around with relatively high velocities that will suppress the Bondi accretion rate. And that will prevent them from accumulating in the denser parts of the galaxy over time. They're just going to continue with like a population with a very large velocity dispersion. So that there could be large kind of suppressing factors there. Lower mass.
Definitely.
All right, we're 10 minutes over time. Let's continue the discussion online.